All right, folks, let's start. This is Dr. Yuzo, EC 360, and this is our fifth lecture. And according to the Gantt chart, we are here now. Okay, we are here at this particular cell, the Wednesday, week 3, and the very first lecture for module 3, block diagram. Can you guys hear me well? And seeing my shared screen, is it clear? The voice wasn't very good yesterday in my another class, but how about now? Is it clear enough? Audio? All right, no easy. Good. Thank you. So let's start. Okay. First of all, a little bit left from previous module and regarding the physical system or say component frequency domain modeling. This is actually a DC motor. Yeah, this is DC motor stuff. And I don't know how many of you ever learned DC motor and DC motor drive knowledge, but these are the basic equations, that the basic principles we know about the DC motor in time domain, of course. For example, the back EMF equals to the constant times the speed, and then this is the ammeter KBL equation, and also the motor torque is proportional to the armature current, and the mechanical part of the system is the net torque equals to the inertial times the derivative of the speed, etc. So by applying the Laplace transform, we obtaining the frequency domain corresponding equations. Okay, I label them from 1 through 4. Okay, and based on which we are deriving is actually this, deriving the introduced output load position angle, angular position angle as output versus the input, which is defined as armature voltage. In other words, input, output, pretty much is studying the transfer function between these two variables. Assuming given input of armature voltage and what is the corresponding output position rotation angle. Okay. This is the transfer function we're studying. And obviously, we defining the input and output at the beginning, and then targeting on this goal, we go ahead to derive the relationship by step-by-step procedure like this. And obviously, by this recorded lecture, you will be able to come back to see the details. But basically, the key is here, applying Laplace transform on the time domain equations. We come up with the frequency domain equations. And then from which we derive the transfer function in frequency domain as well. Okay, every variable is in terms of S, function of S. So if you're interested in a real system analysis, a real system modeling, you can go into this and then let me know if you have any questions. Since this is not the most important knowledge in our class, so I leave this as a notes for you to have a kind of supplemental material to study. Okay. Well, let me know if you have any questions. Okay. Now let's start our module 3, new module. New module. The block diagram. Regarding the block diagram. And the representation. So what this module is about, okay, what this module is about, a couple of things here. First, complicated system obviously always consists of multiple so-called subsystems. And each subsystem is modeled or say represented by a what? Transfer function. Okay. Your subsystem is a transfer function that's modeled by a frequency domain transfer function. Okay. This is what we did pretty much in previous module 2. Okay. Modeling the subsystem. And then this subsystem comprised of a complicated overall system. Okay. So due to this, so this module or say this topic will learn what? How to combine all subsystems to one so-called total transfer function. Okay? Total transfer function. There are multiple systems, multiple transfer functions. They are individually the block is a block transfer function block like this. Maybe the individual transfer function subsystem transfer function is named as G. It has input, one output. You have multiple of them, and they are interconnected, right? Somehow, and then this module can learn how to combine all of them to find out the total transfer function. Okay, this is what this module is about. Okay. So let's learn the basic one first. Obviously, we need to understand what does it mean by block diagram, right? So composition of a subsystem, block diagram. We are not seeing any yet, but first of all, what we could have is we definitely have a subsystem transfer function, right? Which is a function of S in frequency domain. We definitely have a transfer function. Look at this, just a G or any other name. And then because of this, we definitely have input and output signals. Here, be careful. This is signals, not transfer function anymore. Okay, input and output, they are called signals, not input and output transfer function. Okay, be very careful. Don't confuse them together. Okay, this is signals. Obviously, one transfer function, we definitely currently have one pair of input and output. Right? And what else we could have in the block diagram? Summing junction. Summing junction, what is it? Okay, it looks like this. Okay, a circle containing a cross inside. It's called summing junction. What summing junction can do? Summing junction is just a sum up. Of course, here, be careful with either positively or what? Negatively. Okay, negatively. That's absolutely possible. Okay, maybe all of the inputs are kind of doing subtraction. Okay. Summing them up, signals from different blocks into the summing junction to generate one output to next block. So imagine what? So summing junction might have multiple input signals. However, only one what? Output signal. It's a very important characteristic of this summing junction. Okay. If in your analysis you find that doing something like multiple output of the summing junction, there's something wrong there. Okay, there's something wrong. You can only have one and only one output signal. The inputs, of course, very likely to be multiple. Okay. The last thing you could have is called the peak off point. Nothing but just a point, a dot. What this guy can do, what this guy can distribute one to different blocks. Here, very important, undiminished. And similar to the summing junction, what we could have? We definitely only have one what? Only one input to this point. However, we very likely to have multiple output. Okay, so very important. Be careful, these two things, two characters for summing junction and peak off point respectively. All right. Does it make sense? Summing junction, of course, is a multiple signals summing up together and then come up with one unique result. A peak off point is one single signal and then distributed to different places, right? Different blocks. So the output going to be multiple, right? Be very careful. And then how we really conduct the because here we are mentioning one term combine all of the subsystem transfer function together, and then we need to learn how to do this combine. This combine is kind of an operator or say operation. So we need to learn the algebra, which is the basic block diagram algebra. Basic block diagram algebra. Okay. Let's see how close or how similar this kind of algebra with our general math algebra. Okay. We have different. We could have different scenario. Okay. The first one we call it cascade blocks. How to deal with the cascade blocks. Now we are first time in this class see the real blocks diagram. So what does a typical cascade blocks looks like? You have input, right? Let's assume the input as R of S going through the first transfer function block G sub 1 of S, and then goes through the second G sub 2 of S, and goes through the third one maybe G3 sub S, and then come up with the total output signal, which defined as capital C of S. Right? So this is a total system look like cascade blocks. Okay. And then what is the total transfer function. First of all, what do you mean by total transfer function? We need to keep in mind one concept, okay, before here maybe. To any individual block, we have something like that. And then we have input, we call it R, output as C. What do we have? We always have the definition of the transfer function, which is G equals to output over input. And therefore, what do we have? If you really care about output, it's equals to what? Input times transfer function. Yeah. Just as easy as this. Yeah. The transfer function is very easy to be considered as what? We learned from the electronic circuit class. What is it? Transfer function is nothing but what? In electronic circuit. Amplifier circuit. Anyone can recall anything?
Yeah.
Very good. Just a gain, nothing but gain. Okay. Remember, in the electronic circuit, amplifier circuit, we learn what? Cascade amplifier. Remember? A transfer function is nothing but the gain back then. Okay. Now we are talking about a more generalized definition, of course, including the gain concept, because back to then, the gain there was actually a constant in 318. And in 358, the gain is the frequency domain, frequency dependent transfer function, or say gain. So let's see what is the total transfer function, which means this capital C divided by this capital R. What is the total transfer function, right? So how to analyze this? So not something very difficult. So we need to first of all define the middle signals x1 and x2 respectively. And then first of all, 1 equals to what? From here on, we can kind of ignore the parentheses of s to save some time. X1 equals to what? According to the red color up here, x1 is nothing but r times g1, right? Similarly, x2 equals what? x2 is the output of the g2, and therefore it equals to the input of the g2 times g2. Input of the g2 is x1. Right? Similarly, c equals to what? x2 times g3. What can you do is, in the second equation, you substitute x1 by the first equation, so it then end up with this. And in the third equation, you substitute x2 here by the second equation. Therefore, you end up with, does it make sense? From which you can derive easily the total transfer function of the cascade blocks, just equals to, once again, C over R equals to the product among all of the individual blocks transfer function. Does it make sense? Exactly the same result as we had back in the electronic circuit class. Remember, cascade amplifier, what is the total gain? Product among all of the individual gains. Remember, not sum, but product. Okay. All right, this is the cascade. And of course, we can also say the above system in black cascade, just the equivalent to what? Just the equivalent to G times G2 times G3, and here we have R and C. Second case is obviously after cascade, we always gonna learn parallel. Parallel. And parallel, what does it look like? It's involving the peak-off point and the summing junction. Otherwise, you can't do this so-called parallel. Once again, if you're assuming 3 signals, 3 branches, input signal R goes through this peak-off point to reach G1, G2, and G3, 3 transfer functions. And then the results of those 3 transfer functions going to a summing junction to come up with the total output C. Okay, this is how we understand this. So as we said, summing junction could either positively or negatively sum up the signals. So here we label them as positive, negative, and positive, negative. All right. Again, either positively or negatively. Okay. Either way works. Either way works. Then what is a total transfer function? Once again, that's capital C over capital R. What is total? So once again, we need to define the signal in the middle to derive the relationship. So R goes through a peak-off point, and then what is the signal here? Here and here then. What is the signal here? Anyone knows? R. Yep, Jeff is right. How about here? R again. How about here? R as well. Of course, why? You have a signal going to peak-off point. Output of peak-off point are RR. Remaining as the same signal. Why is that? Anyone knows why? Anyone knows why is that? Abbas said is the same node. Well, the same node Y is this way then. But speak out. Okay, that's much more efficient.
Because we want to combine all these parallel transfer function later into one junction, right?
No, we are talking about here. YR and
Okay.
R and R. It's not transfer function, the summing junction yet.
Is the signal a voltage, not amps?
This no, we don't want to do this analogy. No, we don't want to link to it's a clever connection, but however, no, we don't think in this way. They don't think in this way. It's not voltage or current. No, that's not the how we differentiate this.
What about thinking of it like a distribution?
Very good. I hear the I saw the actually. I'm sorry, Kevin. I saw the correct answer from Noah. You need to go back to here. Like I said, very, very important. So here, in the definition, or say the instruction of this peak-off point is clearly telling us it's undiminished, diminished. That after this peak-off point remaining as the input, R and R. Very good, very, very good. Noah is right. Great. Okay. And then the signal here, we can define as X1, X2, and X3 here. So once again, X1 equals to R, G1, X2, RG2 X3 equals to RG3, right? And then C equals to what? This is summing junction. X1 plus minus X2 plus minus X3. Right? So this is the C. And then now we link the C to R by substituting X1 through 3 by equation 1 through 3. So we are ending up with R times G1 plus minus G2 plus minus G3. Right? Therefore, the total function equals to total C over total R, and then equals to G1 plus minus G2 plus minus G3, right? So summing junction is doing really summing up job. And this parallel blocks, be very careful how to identify this is a parallel connection. This is actually harder than the identification in purely circuit. Okay, it's not very easy. Students keep making mistake actually. How to identify the parallel connection. Pick off point at the beginning to separate a signal. Summing junction at the end to sum up all of the resulted signal. This is parallel. Okay. This is parallel. So this identification is very important because after the identification, or say after knowing it is parallel connected, we are able to come up with this conclusion, just to sum the transfer function up, right? Before this result, we have to, again, correctly identify the connection. Is it parallel or something else, all right? Of course, after this, is G1, G2, and G3 like this. Okay, the equivalent system, total system block diagram is like this. One input, one output, of course, only one single total transfer function in the middle, right? This is a cascade and a parallel. Cascade and a parallel. You need a minus in front of G1. Oh, Noah just bring up a question here. Plus minus in front of G1. Very good point. Very good point. I have to admit it. I have to admit it. Okay. To admit it. In other words, here we have plus minus. Very good point. That's a very, very good point. Fully agree. Fully agree. Fully agree. Excellent. Thank you, Noah. This is absolutely very good point. As well as here. As well as here. Excellent. Excellent. We have 3 plus minus here. So should be here, here, and here. Correct. Correct. Well, and here. Well. All right. And here I am.
This is like, what if you had essentially 3 different amplifiers that were put in parallel? The voltage will essentially, like, say, let's say you had a transfer function.
A superposition, then obviously superposition.
And thus, that's why we would get 3. Like, let's say, we sent some voltage signal in at an amplitude of, I don't know, let's say 1 volt. And then each transfer function, like, let's say they were all the same. So they're all G1, and G1's transfer function is 2. So we could multiply that by 2, and then we're having 3 summing junctions for 6, correct?
It sounds about right, but I'm not quite following the details, but the idea sounds right. Yes.
Okay. Okay.
Yep. Yep. By here, you're going to do superposition. Yes, purely superposition by here. but I barely. I see a lot of cascade, the amplifier, cascode, or cascode. However, never seen a parallel amplifier design. That's a little bit weird to me. Have to admit.
They wouldn't do that for higher power or something like that.
Why you're doing that why you're doing that in higher power? Why?
Because like if one specific transistor can't handle it, wouldn't you need multiple?
Then why not cascade?
Well, why not cascade before, parallel after, and then put total transfer function together? You can do that, right, or no?
Well, never see why we need to do that. That's my point.
Oh,
Because if you feel like your power is not big enough, your voltage, your gain is not enough. Okay, cascade. Cascade is not enough. Is not enough. Or cascade more.
But if you need to drive a load, for example, let's say from a smaller transistor, you only have
you're increasing the current rating to increase the power.
I
Well,
guess, distributing the power so that way one transistor doesn't blow. Instead of running it all through one. Is that when we would want to put parallel blocks?
in my experience applications, what I'm gonna do is choose higher power amplifier instead of parallel connect. Yeah.
Okay, I see what you're saying. All right.
Yeah. So it sounds doable. However, no experience on this particularly. No parallel amplifier. No. All right. And here, Sawyer is asking, is parallel the same as I'm sorry, I don't even know that word. Concatenate. What? Never heard of this name before. But yep. Let me see. The opposite of cascade. The opposite of cascade. The opposite of the cascade, meaning what kind of connection that is. Is it parallel? Well, they always appear in pair, right? And so are they opposite? Well, it's a little bit English problem. I would say only two categories. Obviously, two categories. Just like the connection of the in the circuit, right? Either series or parallel. Oh, I see. That's fine. That's fine. Anyways, this is the cascade and the parallel. Okay. Be very careful how to identify them first. Okay, cascade is fairly easy to be identified. However, the parallel, well, it's not actually that easy, but through examples, you will see what my point is. Okay, one peak-off point and one summing junction at the end. Okay, we will see. Now we're gonna learn the third possible connection. Okay, third one is what? Third one is, here we go. Looking for my notes. Feedback. Okay, feedback is one of the basic connection. Okay, one of the basic block diagrams. What does feedback look like? One signal, defined as R again. In parallel, the signal go into a peak-off point, right? However, in feedback, the input go into a summing junction. Okay, this is the major difference between these two. Okay, it's very easy to confuse these two. Okay, and then after the summing junction, you go through a transfer function we call a G, and then get the output C. So-called feedback is happening here. Okay. Obviously, this is a feedback transfer function, H. And here, we might have positive feedback or negative feedback, okay? Again, once we have the subinjunction, the input might be either positive or negative. However, the input, generally speaking, is positive. Okay, well, sorry, I forgot the use the black color to color code it, but you understand what I mean. Yeah. All right. So here to analyze, once again, the total transfer function, output C over input R, okay, to find out what is the total transfer function. And what we can do is like this, defining the middle signals. So here, this signal, we define it as E, capital E, meaning error signal. And then what this signal is, this signal is what?
Just the output, isn't it? The output signal.
Just the output, nothing but the output signal. And what this signal is?
Just the output, because it's diminished.
Still the output. That's right. Okay. And by the way, it's not a stupid question. Okay, it's really, because this is easy. You can easily tell. However, we're trying to go to the original definition. Peak off point, one output of it is C. Then the input has to be C as well. And the other output of it has to be C as well, right? That's why C, C, and C, okay? Because we're seeing three signals pretty much. Because of the peak off point, they're the same one. They're identical, yeah? And this signal is what? This signal is what? It's called feedback signal, to be compared with input, R. So based on which we can derive now E equals to what? E is equals to R plus or minus F. And further equals to R plus minus F equals to what? Input times transfer function, which is C times H, right? On the other hand, along this path, output C equals what? Due to the G here, due to the transfer function G here, C just equals to E, error signal times G, right? What we need to do is substitute E by, in the second equation, by the first equation. So C is equals to G times R plus minus F. And F, let's just use C times H. Any questions so far? Is everything clear? If so, then we can derive what? C equals to G times R plus minus C times H times G. Further, what do you need to do is move this term to the left-hand side of the equation. End up with 1 minus plus HG times C equals to G times R. I don't know if this makes sense. Here is plus minus. Because you move this term to the left-hand side of the equal, that's why you end up with negative positive backwards, right? And then you combine this term C. That's why you got C times parentheses 1 minus plus GH. Okay. Does it make sense? now, of course, the total transfer function, which is C over R, just equals to G divided by 1, once again, minus plus GH. This is the feedback system like this. Total transfer function. Yeah, very useful, very useful. Feedback transfer function, what is it? It's like this. And once again, I want to emphasize here. This is pretty much as positive feedback and negative feedback respectively. Gonna introduce the denominator here, negative here, and the positive here, respectively. Okay, the positive, negative here is negative, positive. The other way around. Is that clear? Any questions? In other words, if positive feedback here, your denominator equation or say formula is 1 minus GH, right? If negative feedback here, then you have 1 plus G times H in denominator. Right? Any questions? This feedback is the most important one. Okay, this is the most important one. And not only used for this module, but also through the entire course. But besides, such kind of feedback system has two very important concepts here. One is called closed loop transfer function. Another is called open loop transfer function. Yeah. What are the definitions of them respectively? Okay. These need to be very, very clear. This need to be very, very clear. The closed loop transfer function of this feedback system is nothing but the total transfer function we just derived down here. Closed loop transfer function means nothing but the total transfer function. However, to this feedback system, we also have another open loop transfer function. Okay, it's a feedback closed loop system. However, it has an open loop transfer function defined, which is nothing but G times H. Okay. These two concepts are very, very important. Okay, you don't want to miss. Okay, and is pretty much the open loop transfer of a feedback closed, because this is called closed loop system, right? Since it has a feedback here. Closed loop system, however, it does have an open loop transfer function. Okay, don't be confused. Okay, it has closed loop transfer function. It also has open loop transfer function we can define. And the open loop transfer function is equal to the product between G and H. And then how to define G and H then? G is called forward transfer function. Okay. Forward pass, you see? Forward pass here. It's G. H is what? This is easy. It's a feedback transfer function. So 1, 2, 3, 4, 4 concepts here are very, very important. And once again, feedback system is the most important one, most important concept or structure we're gonna use. Any questions? Is everything clear so far?
Why was the open loop transfer function just GH?
It's defined as the forward transfer function times the feedback transfer function. defined as so.
Okay. Oh, that's because F would be broken, and that would be the output. Is that why? Or?
If feedback here is broken, and then
that's open loop, right? Or no?
Yes, that way gonna be open loop, and the open loop, and then F gonna become the output. Yeah, that's true.
So then it's just G times H. Okay. Well, why isn't it? I guess if C was our main signal, why is it that now it seems like C became the feedback, the end of the feedback?
What do you mean by that?
Because if C is at the output of G,
At output of G and
you were to break the line of F, the feedback line, why would the output just be G, or the transfer function just be G? Because H isn't going anywhere at that point.
The transfer function gonna be G times H, not G itself. Because in that way, you're F as the output.
Oh, not you immediately assume that you're going to be hooking the output at F. So basically, correct. C would go to F.
Because you open here, right? You open here, and the C becomes the middle signal rather than the output. We won't define that way.
You know, okay. Okay. Yep. Makes sense.
All right. Yep. Right. Yep.
I'm still a little confused on what H is doing in the open loop. Would you mind explaining again? Sorry.
And the open loop means John is proposing, well, if you open here, that means the system becomes like this, right? It's, R remains, some injunction, E remains, G remains, C remains. C remains. However, keep going to H and then to get signal F. Now this system is open loop. Open loop, and then to this system, the total transfer function is equals to output, which is F, over the input, which is R. And this is pretty much G and H are cascaded.
Can you scoop that up for us, please, so we can see?
Oh, sorry. Here.
Yeah, that's what I was looking. Okay, yeah, that makes much more sense.
Yeah, and total transfer function now it becomes a GH. So John's point is why we are defining G times H as open loop transfer function. Because if you break the feedback here, the system now becomes open loop. And the low open loop transfer function is what? Is equals to output over input, which is F over R. And then that is nothing but G times H. Yeah, basically his point is right. His point is right. Okay. Is that clear, everybody? All right, if it's fine, then we move on to one small example. Let's see. Let's do an example to really a small example. Let's assume a system like this. Now find closed loop transfer function and open loop transfer function. By CLTF, I mean closed loop transfer function. And what I'm saying is here, CLTF, this is OLTF, okay? So to this example, find these two respectively. Let me give you guys a kind of 5 to 10 minutes, okay? And then I will present the solution. According to the algebra about the cascade, parallel, and feedback, all of them together derive what is the open closed loop and the open loop transfer function of this system. Okay? And of course, here is 5. Okay, this is number 5. Here is S. Here is S2. All right. All right, go ahead. So obviously, we can see in the forward path here, we have 5 and 1 over S plus 1. These two are what? Cascade, right? So is 4 and 1 over S in the feedback loop, in feedback pathway, right? We have forward 2 transfer function in cascade, feedback 2 transfer function in cascade as well. We need to do this simple combination first, right? A little bit hint and keep doing. All right, we can take a look together. So basically, as we said, forward path, these two are cascaded. So is these two. So eventually, we can have an equivalent system like this, right? Cascade means what? Product. 5 over s plus 1. Then feedback here as 4 over s, right? And the negative feedback, okay. Don't miss this sign. This matters. It matters to the denominator formula, obviously. Okay. This is a resulted system, which is the basic feedback configuration, right? One forward transfer function here, one feedback transfer function here. So in your head, you correctly identify this as G. This is H. And then what we need to do next is just applying the formula, right? Negative feedback, of course, that is, as I said, very important. So the closed loop transfer function, which is total transfer function, right, equals to numerator is G. Denominator is what? 1 plus, right? Because of negative feedback. 1 plus G times H. So it equals to does it make sense? You leave the result like this. Actually, I don't mind in the exam. Okay, you leave your last final result like this. It's all right. In the middle step, you probably don't want to do this because it's too messy. However, this kind of result is enough. But if you want to go further, then you can do it. So numerator remain, and denominator is what? It's s times s plus 1, and then here is time s plus 1 plus 20, right? So finally, and then here it cancels, and then the result is going to be s plus s1 plus 20, and 5s. Does it make sense? An open loop transfer function, according to our definition, is G times H, and then G times H. That's it. Right? So take a look at this and then see any questions you have. Any questions we need to discuss more?
So S would be, in this case, a frequency, right? So this would be the frequency of our signal that we're sending in, correct?
No. S is not equals to frequency. It's equals to omega times J.
Okay. So that would be the output in terms of, but if you know omega, right, you would just get a complex output, right?
I'm not quite following. What are you trying to ask?
Never mind. I'll figure it out.
All right. Or by another time to discuss further, like the office hour. Okay. And any other questions regarding how to do this? Any step? Everything again is based on the provided basic concepts. You're clear on these concepts, then you should be fine. Okay. So clear on these concepts, you should be fine. And then what matters is correctly identify or combine who is G, who is H. G is along the total transfer function, we're saying, along the forward path here. H is the total transfer function along the feedback path here, right? With G, who is H. Here, Lucas asking, what is the difference between between Laplace transform and Fourier? This is a question regarding the knowledge we learned, actually, because this course is not about Fourier transform, but who can answer this question? What's the difference between Laplace transform and Fourier transform? And also Z transform. A Z transformer could probably a little bit far to you guys, but let's just discuss the Laplace and the Fourier. What's the difference between them? Anyone knows? So you're saying is one is integral, another is averaging. Well, it's a little bit. Well, let's talk about, because they have difference in terms of different aspects, right? Let's just talk about what they are for, respectively. How about that? Laplace transform is for what? Fourier transform is for what, respectively? Because if we know what they are respectively for, then they become easier to understand, I guess. Anyone can speak out. Typing is really tired for both of us. Tired for me to see and tired for you to
Are you saying, like, Professor, the difference between, like, it would be the Fourier transfers for, like, signal analysis, and Laplace more of, like, solving different differential equations?
No, this is a question I should ask you. What do you mean by difference? Because you're wondering what's the difference between two, right? And I'm saying, well, let's first of all discuss the what they are for, respectively, right? However, what's exactly you mean by the difference? What difference you want to know?
Isn't Laplace more precise?
More precise for what? Again, what they are for, respectively. What they are for.
Analyzing signals.
Analyzing signals. It can be, of course, eventually can be used as to analyze signals. However, Laplace transform is basically a tool you can use to do a conversion between time domain expression and the frequency domain model. Okay, this is Laplace transform. It's a conversion tool between time domain and frequency domain. Fourier transform is what? Fourier transform is more of signal analysis. Randomly given a signal containing multiple different signal components, say DC, AC, and inside of AC you have fundamental and harmonics, a kind of mixing signal, and then you are looking for the magnitude of each component. You can conduct Fourier transform. You can pretty much break the total mixing signal into different components, different categories, and see how much it contains. And at which frequency you have how much magnitude. Okay, so this is Fourier transform and Laplace transform. Does it make some sense? Is this what you guys learned before, or is it clear? Any comments, any questions about these two? And by the way, what made you pop up Fourier transform? And what made you pop up with the Laplace transform at this point? Since we have done Laplace transform last module and we never talked about the Fourier transform in this class yet, and then what made you have such question, Lucas?
We were talking on 450 about it, and
During
I
lecture?
wanted to understand the complete difference between both of them. I knew they weren't equal, they weren't the same thing, but I know both of them you transform into the frequency domain, but you use them for different things. So I just wanted to make sure I knew exactly what the difference between both of them are.
Okay. The Fourier transform is pretty much you're analyzing each frequency component. The signal component is defined as signal with different particular frequency. So that's how you link with the frequency in Fourier transform. Okay. And the Laplace transform is converting back and forth between time domain and frequency domain model. So in 450 signal processing, you guys more, I think, both you're going to use both. But if you're analyzing the component, the composition of a signal is more of Fourier transform.
Okay, that makes sense.
All right. Okay, so now the rest of time, we can begin with the next thing a little bit and leave the major thing to next Monday. Block diagram algebra. Well, so far we just learned 3 basic types of block diagram: cascade, parallel, and feedback, and their corresponding total transfer function. And fairly easy. However, in a complicated block diagram, okay, you might have come across many of them, multiple of them, and mixing together. So here we can learn how to conduct the block diagram to that kind of overall system. So the algebra here is, first of all, is pretty much a moving algebra. Here, explain a little bit the moving. So this block diagram algebra is basically meaning how to move the block. Okay. Move the block. You can learn this. Be very careful. Here we are talking about block, how to move the block, rather than how to move the peak-off point, nor summing junction. Okay, listen very carefully. This is a very, very popular mistake in this class. We are moving block. We are not moving summing junction or peak-off point. Okay, be very careful which one you're moving. You're moving block. And of course, why we need to move the block, anyone knows? Why we need to learn how to move the block, given the system? Why we need to learn how to move the block? Move the block around for what? Anyone can imagine? Why? Anyone? Any guess? can guess, well, given the system, many example. Give you an example we're gonna conduct next lecture like this. You see how many blocks here connected in certain ways, right? So my question is why we need to do the moving, why we need to move them around. Any possible reason you can imagine or guess?
Make them cleaner.
Cleaner. Well, guess what? Such kind of connection, no matter how you move, it won't be cleaner. I mean, or say you move, and then why it become cleaner? It's not the look. Obviously, that's not the look. It's not for the better look. We are doing combining, okay? And always remember, we are doing combining, trying to eventually find the total transfer function. To achieve that, we have to do block moving. Because to find or combine what? The three basic block diagram. Okay, this is what we are moving blocks around for. Just to find or say do some combination so that we can see the three basic block diagrams we just learned. Okay, who are they? Cascade, parallel, or the basic feedback. Okay. Without moving around, we are not able to directly, or we're not able to easily, completely see the easy cascade, parallel, or feedback. Okay, that's why we need to move around. After moving, we can see, we can see a cascade. Combine them, very easy. Then two blocks, maybe more, even more blocks becomes one, right? Because we can do the combine. If after moving, we can see the parallel, okay, another combine. The multiple blocks becomes one. Does it make sense? This is how we step by step really combining the complicated system block diagram. Okay, this is the idea. All right. Move around so that we can find, we can combine, we can see the basic ones we learned. These three. Okay, no more. Okay, basic ones, no more. There's no other basic ones. Somehow come up with one of these three, and then do the combine according to what we learned today. Yeah. That's going to be very easy. However, how to move? How to move the block? In other words, how to answer this? Follow. Moving algebra, or say the block diagram algebra. Okay, algebra. We have four algorithm for operation to do. Is a move one block. Okay, one block at a time. Okay, you're not doing more than one block at a time. You're not moving more than one block at a time. Okay. Move one block. This is from input side to output side of a summing junction. This is the one. We have up to 4. This is the first one. Move one block from input to output side of the summing junction. The next, move one block again from what? Output to input side of summing junction. Third one, move one block from input to output side of whom? Not difficult to guess, right? Pick out point. And who is the last one? Following this pattern, you know easily. Move one block from the output to input side of pick out point. Okay, we can learn 4 algorithms. Can't do anything else, okay? Can't do anything other than these 4. Okay, we are moving. So first of all, we can't move. We cannot move a summing junction. We cannot move a pick out point. We are moving block, and we are not moving more than a block at a time. And we cannot do anything else other than these 4. Okay. Right. So we will see what are they specifically. Okay, by next lecture. All right. Thank you for attending today's lecture, and talk to you guys on Monday. Bye now.